Okay, let's continue our discussion. So here we have a uniform rod of length 200 centimeter and mass 500 gram, and it is balanced on a wedge placed at 40 centimeter mark. A mass of 2 kg is suspended from the rod at 20 centimeter, and another unknown mass M is suspended from the rod at 160 centimeter mark as shown in the figure. So here we have the figure. This is the block and this is the wedge on which this block is placed. One mass is suspended here, another mass is suspended here. So we have to find out the value of M if this rod is in equilibrium. So if this rod is in equilibrium, net force as well as net torque should be zero. So to get this rod in rotational equilibrium, rotational equilibrium, net torque should be zero. So let us find out what are the forces and where are they acting. So here we have 2 kg. So we have a force acting here of 20 Newton force. Let's say this is F1. Why I am saying 20 Newton? Because mass times acceleration due to gravity. G is given here as 10 meter per square second. So 20 Newton force. Now here at this end, there will be a force acting downward, which will be 10 times this M. Okay, let's say this is M prime. So 10 times M prime Newton. Now, this rod has mass 500 gram, so which is 0.5 kg. So its mass we can consider to be concentrated at its geometric center because this is a kind of uniform. If not given, we will take it as uniform rod. So here at the mark of 100 centimeter from this end at 100 centimeter, we can consider its weight. Let's say it is force F3 and it will be 0.5 kg times 10, that will be 5 Newton, and there will be a normal reaction at this point balancing all these forces. Let's say this is R. So this R will be how much? 20 Newton plus 5 Newton plus, look, 20 Newton plus 5 Newton plus 10 M prime. Okay, this much Newton. Now, if this body is in equilibrium, that is in rotational equilibrium as well as translational equilibrium. So, to keep this body in rotational equilibrium, net torque should be zero. So, what are the torques acting on this body? Let me write these forces and their point of action at different place here. So, this is 0 centimeter mark, and from here at 20 centimeter, there is a force acting downward which is 20 Newton. Another force further at 20 centimeter, another force is here R, and further on a 60 centimeter, there is a force of 5 Newton acting here, and then there is another force at, this is 20 20. So 40 centimeter we have covered, 60 100 centimeter we have covered, so another 60 centimeter is here, so that from here to here it will be 160. So here we have 10 M prime Newton. So, and at this end it is completely 200 centimeter. This is the last end of the rod. Okay, now we are free to choose the point about which we can take torque because we know torque is independent of choice of reference point. So it will be better to choose here. At this point, we are choosing reference, and about this point, we are going to take the total torque. So about this point, due to this force, let's say there is a torque tau 1, and this force will be perpendicularly outward. The direction of this torque will be perpendicularly outward to this plane in which this screen is lying. So, and due to this direction should be inward, and due to this the direction should be inward as well. So you can check it by uh, here, you can check it by right hand rule. So if you do R cross F with your right hand, so the thumb will be indicating outward, and in these two cases the thumb will indicate inward. Now if this is in equilibrium, net torque outward and net torque inward should be equal. So net torque outward, what is the magnitude? So tau 1 can be written as r cross f, that will be r sine theta. Its magnitude will be r sine theta, and theta is here. Look, this is the direction of position vector. So theta is 90 degree. In all the cases, theta is 90 degree. These two things, r and f, are perpendicular. So we can write rf sine theta as rf sine 90 degree, which will be only rf. So r is here 0.2 meter. I am converting it into meter. So 0.2 meter into 20 Newton equals to this torque. So this will be 0.6 meter into 5 Newton. So, and this will be, let's say, Newton meter, and this will be 1.2 meter times 10 m prime Newton. Look, from here to here it is 60 centimeter. Further 60, it will be 120 centimeter, that is 1.2 meter times 10 to the power m prime. Now, this will be 4 Newton meter equals to 3 Newton meter plus 12 m prime Newton meter. So, here it will be 1 Newton meter. I am just subtracting 3 Newton meter from both sides. So here it will be 4 minus 3, that will be 1, and here this 3 will be gone. So it will be 12 m prime Newton meter, and then m prime will be 1 by 12. And if this quantity is mass, it should be 1 by 12 kg. We are getting here m prime as only numerical figure because in this Newton we have considered its mass in kg already. So there is no need to worry about that. So here we have the answer. Mass of this body should be, this should be 1 by 12 kg. Let's check if it is there or not. So yeah, it is here. It is here. Okay. So here we have a circular ring of mass m and radius r, and an arc corresponding to a 90-degree sector is removed. The moment of inertia of the remaining part of the ring about an axis. Okay, let's continue here. So let's say we have a circular ring here lying in xy plane, and let's say this is z-axis passing through its center. So the moment of inertia about this z-axis will be I equals to m r square. Now, what happens? There is a removal of its part, and the length of this arc being removed is corresponding to the length which is subtending 90-degree angle at the center. So, in short, we have removed 1/4 of its circumference. So now we have new mass here, and let's say this new mass is m prime. This new mass is 3/4 of its original mass. Okay. Then new moment of inertia will be 3 by 4 m r square. Now, why I'm saying that this is 3 by 4 m r square? Because look here, let's say we have to obtain moment of inertia of a particle of mass m1, and which is at a distance of r. Then the moment of inertia will be m1 r square. Let's say we have another particle and it is also at a distance of r, and its mass is something m2. So it will be m2 r square. Again, if we are continuing our argument by adding such particles of masses m1, m2, m3, and so on up to mn, so that we are forming a ring, actually 3/4 of the circumference of a circle or ring in this case. So we are forming a body here, or a linear mass distribution, which is equivalent to this ring, remaining part of this ring. So in that case, if let's say we are choosing n number of such masses, so here mn, and it is also at a distance of r. So we have to add all these things this way, and then we will have m1 plus m2 plus up to mn, and r square will be common. And this summation is nothing but the total mass of this part of the ring. This is what we have here. So we can write this way. Now we can write 3 by 4 mr square, or we can write, yes, we have to check what is the coefficient multiplied with this mr square. So this k will be here 3 by 4. Okay, this is what multiplied with. So this is your answer here. To the next question. So here we have given two particles of mass 5 kg and 10 kg respectively are attached. So let's say here we have mass m1 of 5 kg and another mass of 10 kg. So let's say it is attached with this massless and negligible mass, and mass of this particle is 10 kg, and this rod is of negligible mass and rigid. So let's say we have to obtain center of mass with respect to this 5 kg, means how far the center of mass will lie. So let's say this is z axis and we are keeping this 5 kg mass at origin, and let's say we are keeping this rod along y axis. So this is y axis. Okay. So in this case, m1 is 5 kg and y1, that is position vector along y axis, or the position simply along y axis of this 5 kg mass will be 0, and this 10 kg mass will be at 1 meter as given in the question. And again, let's say the center of mass is lying at a distance something y from this 5 kg mass. So we can write y equals to m1 into y1, which will be 0, plus m2 into y2. So m2 into y2 will be 10 and unit will be kg meter, and then divided by sum of these two masses, that will be 15 kg, and it will be 2 by 3 meter. And if yes, you have to convert it into centimeter. So this will be 200 centimeter divided by 3, and if you can solve it, it will be 6.66.666 so on. So this is nearly 67 centimeter. Now coming to the next question. So we have to obtain torque about the origin, and force is given and position vector is given. So this is 3j cap and this is 2k cap. So we can obtain it directly. So this is torque equals to R cross F. So we can write it, R is given 2k cap meter cross 3j cap Newton. Okay, so 2 times 3 will be 6. K cross J will be minus I, and this is unit of SI unit of torque. So this will be minus 6 I cap Newton meter. So here we have the option for this. So this is all for this video. In the next video, we will start a new chapter, and that will be gravitation. So see you.